Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at constructing box plots. So a box plot is just a way to display the 5-number summary. The 5 numbers in this summary are Q0, minimum, lower quartile Q1, median Q2, upper quartile Q3, and maximum Q4. These are the same things we learned in a previous video. So in order to construct a box plot, we first need to calculate the quartiles. So let's calculate the quartiles for these numbers here. So we usually start off with Q0 and Q4 because they're the easiest. So Q0 is the minimum, Q4 is the maximum. So Q0 is 7, Q4 is 14. So next we have to calculate the median. Remember from the previous video, we need to calculate the median Q2 before we can calculate Q1 or Q3. So here there are 9 scores. Odd number of scores means that the median is always one of the scores. So the median here is 11. So when the median's one of the scores, you cross it out so you can calculate Q1 and Q3. Now we have 2 equal groups of 4 scores. The median of the lower group is Q1. So the median of these 4 scores, well, the 2 middle scores are 8, so the median is just 8. Q1 is 8. The median of the upper group of scores is Q3. So the 2 middle scores in the upper group are 12 and 13. So the Q3 is halfway between. It's 12.5. Remember, if you can't tell what's halfway between 2 numbers off the top of your head, you just add them up and divide by 2. So here, the 5-number summary is Q0, Q1, Q2, Q3, and Q4. We are going to display these using a box plot. Its actual proper name is box and whisker plot. So the reason is it has a box and a whiskers. You actually draw a box around Q1 to Q3, and then you extend whiskers to the maximum and the minimum. So for our data here, we start the box at Q1, 8, and we extend it to Q3, which is 12.5, which is about there. So this is the box part of the box plot. So then we extend a whisker to the maximum, which here was 14, and the minimum, which was 7. So there's one more thing we need to do with the box plot. The median is marked with a line in the middle of the box, just like this. So here the median was 11, so we put our median line there. So this box plot displays the 5-number summary, Q0, Q1, Q2, Q3, and Q4. All right, let's now look at parallel box plots. So just as we can draw one box plot, we can draw multiple box plots using the same axis here. We call them parallel box plots. So why would we want to do that? Well, drawing parallel box plots allows us to easily compare and compare visually multiple sets of data. So let's say I gave a maths quiz out of 10, and I have 2 sets of scores, year 10s and year 9s. So I've drawn a box plot for each group, and we can compare the data easily. So note, I drew the year 9 box plot like this because I wanted to make a point. Sometimes when you're drawing box plots, if there is an outlier, it will be marked with an X, and so this would be the second highest score. It doesn't really matter whether you put the outlier outside the box plot or you don't. Not that big a deal either way. So let's look at these 2 box plots and see what we can decipher about the data. Well, we can see, for example, that the year 10s had a higher median for this score. The median for year 10s was 8, and for year 9s it was 4. We know that the top 50% of year 10s scored more than all except one of the year 9s. So the top 50% of year 10s is this range here. This box plot is telling us that 50% of year 10s scored 8 or more. And that's more than all of the year 9s except this one outlier. Another thing you could say about these box plots, the lowest 25% of year 9 scored below all of year 10s. So the lowest 25% of year 9s is here. This section always represents a quarter or about a quarter of the data. So the lowest 25%, the lowest quarter of the year 9 class scored either 0 or 1 in the quiz. And no year 10 scored below 3. Each of these 3 points is making the case that the year 10s scored higher on the test. The scores were generally higher in the year 10 class. We can see that clearly from the box plots. Of course, these are not the only 3 things you could say. You could also say other things. For example, what we see here in the year 10 box plot is that only 25% of students scored 6 or below. This section of the box plot represents a quarter or 25% of scores. But 6, although it was Q1 for year 10, it was Q3 for year 9. That means 75% or 3/4 of year 10s scored 6 or below. 25%, 25%, 25% makes 75. So you could say that the bottom 25% of year 10 scores was the same as the bottom 75% of year 9. There are heaps of different things you could say. Common sense tells us, looking at these box plots, the year 10s did better on the test, and it just allows us to see the distribution of scores. Where did the lowest students score? Where did the bottom 25% of students score? Where was the median? What was the highest score? That's the advantage of box plots. All right, let's now take a look at using box plots to determine skewness. So here we have 3 differently shaped box plots. Let's look at this first one here. Now, here you can see there's a very small range of scores. The difference between this score and this score is low, where here there is a much larger range of scores. But the way box plots work is that this small range and this large range both contain the same number. They both contain 25% or a quarter. So what would this look like if we were to draw a histogram? Well, we would have lots of scores clustered towards the minimum. There are a lot of scores in a small range here, so we expect that they'd have high frequency. But as we're going across and the scores are getting larger, they're getting more spread out. So the histogram might look something like this. So this data, I hope you remember, is positively skewed data. That means the scores are clustered towards the minimum and usually means greater than the median. On the other hand, this box plot is symmetrical. It's about the same range of scores for the bottom 25%, the next 25, the next 25, and the top 25. So we'd expect that this would have a pretty symmetrical histogram. It might look something like this. And of course, if we have a box plot that looks like this third one here, there's a large range of scores at the minimum, so the scores are more spread out. And as we get closer to the maximum, the range of scores decreases. This is still representing 25% of the scores in a small range. So this data would be negatively skewed. Negatively skewed meaning that scores are clustered towards the maximum. It usually means the mean is less than the median. All right, let's have a look now at outliers. So when you have a set of scores, an outlier is basically just a number that is much larger or much smaller than the rest of the scores. It's really important to note if there are any outliers, because then you can see whether they have unduly affected particularly the mean. Now, up until now, we've just been looking at data sets and saying, oh yeah, that score looks pretty big, looks pretty small, it's an outlier. But now we're going to use a rule that is commonly used in statistics to determine whether or not something is an outlier. So this gives us a black and white definition. So we're going to consider a score an outlier if it's either greater than Q3 plus 1.5 times the interquartile range, or less than Q1 minus 1.5 times times the interquartile range. So in this set of data, it might be tempting to say, oh yeah, 0 and 50, yeah, they look like outliers. But let's apply this rule and see if in fact they satisfy the definition. So the first thing we need to do here is identify Q1 and Q3. There are 6 scores. I divide them into 2. So for the bottom half here, 12 is the median, so that's Q1. Similarly, the median of the top half is Q3. So the interquartile range here is 26 minus 12, which is 14. So let's go ahead and check whether 0 and 50 are in fact outliers. So a score will be an outlier if it's greater than Q3 plus 1.5, it's always 1.5, times the interquartile range. So if you put that on your calculator, you would get 47. A score is an outlier if it is greater than 47. 50 is greater than 47, therefore it's an outlier. We will also consider any score an outlier if it's less than Q1 minus 1.5 times the interquartile range. Now, if you put this on your calculator, you get -9. 0 is clearly not less than -9, so it is not an outlier. This set of scores contains one outlier, which is 50. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.